definition, right? So a sequence is a function whose domain is a set of positive integers, right? It's just a set of numbers that are positive. And we will be getting into series a little later, but I wanted to highlight the difference right now. A series also contains a set of positive integers, except the only differentiation between the two is that a series is a list of numbers that are actually added together. That's the key component there. So, for example, if I were to write an example of a sequence could be 1, 2, 3, 4, just a set of positive integers. But a series containing the same set of positive integers would look like this: 1 plus 2 plus 3 plus 4. Do you see the difference? So a sequence just contains a set of positive integers, whereas a series has that operation, that positive operation of addition involved there, right? So hope that settles your mind and gears you up towards the next chapter when we'll be doing series. So moving forward, one of the criteria you must learn in mathematics is obviously symbolic notation, right? And a popular notation of a sequence is denoted by the letter U subscript N, right? So you will see this occurring a lot whenever you are doing topics such as sequences. Now that we understand exactly what a sequence is, a set of positive integers, let's get a little more into detail into the types, because there are various types of sequences, right? And I'll try my best to show you guys some diagrams soon, right? So we have probably around 5 types of sequences. We have a convergent, a divergent, a oscillating. We also have periodic and alternating. I didn't write them in. Perhaps I should have. Right, so we also have periodic sequences, and we also have oscillating sequences. Okay, so let's get into a little bit about the convergent. Let's get a visual understanding of exactly what a convergent sequence may look like. All right, so let me just enlarge this here. Okay, let's just get that straight. All right, sequence doesn't want to obey the rules of computers. All right, so we have the different types of sequences described as convergent being the first one, okay? So this is what a convergent sequence typically looks like if it were to be graphed. And as you can see, the sequence represented by that mathematical notation u to the power subscript n, it's convergent if the values approach a fixed point as n increases. What does this mean? So you sit there and you think to yourself, I read the English, but I don't understand what it means. Well, a mathematical notation for it is represented by the following. You would frequently see the limit of your sequence, u subscript n, as n approaches infinity is equal to L or some number. So let me try my best to explain. Let's just say we had our axes set up nicely here where the x-axis represents the numbers n. So starting from here, you would have the value of n being 0. And as you go along that positive axis, you'll see that the values of n keep increasing and increasing until you go all the way to positive infinity, right? Now, this graph shows that when the value of that x value or that n value increases, right? As n tends to become greater and greater, as n approaches infinity, you'd notice that that graph happens to be approaching. It gets closer and closer and closer to a particular value until eventually it touches. You'll notice it's said to be converging to a certain number L, right? As n goes to infinity, the limit, the function actually has an existing limit, which is a numerical value of L, right? And that value can be found using, in the future, soon you'll be seeing how we can attain this value of L when we actually have a function for u subscript n. Okay, but a convergent series is one that actually has a value. The function converges to a unique, concise, particular value, and that value is denoted by L. It's called the limit, right? It has a limit. So that's for a convergent sequence, what it looks like if you were to have to graph it, right? So let's just move this mister out the way. Okay. See if we can move him for a bit. All right. Now let's get into the second one, which is a divergent sequence. And I'm sorry if I kept on using the word series sometimes. It's so easy to get mixed up with series and sequences because essentially they could be the same. They are highly not, but they could be the same in terms of the numbers they use. It's just that one has an additive operation involved, right? So a divergent sequence. What is a divergent sequence? Well, we saw what happens with a convergent sequence. As n approaches infinity, the numbers get closer and closer to a particular value. Look at this graph here, right? Look at this graph right here. My computer loves giving problems. All right, so we're looking at this graph here. Now, if I were to say what happens as n were to go to infinity, right? So as n gets larger and larger and larger, what do you see happening with this graph? Well, initially, when n was 0, the function was very close to 0 as well. And as n started getting larger and larger and larger, you notice that that function is diverging. It's just getting bigger and bigger and bigger and bigger, and it's infinitely bigger. Like if I were to continue this function, it probably would eventually approach positive infinity. Similarly, if you had a graph reflected below the x-axis, that function would also diverge to negative infinity, right? So a divergent sequence is one where it's not convergent, obviously. It does not converge to a particular number, and one of two cases can happen. The divergent sequence can diverge to positive infinity, as in this case here, or it could diverge to negative infinity. That's if it were below that x-axis, and as n similarly was approaching infinity, it were diverging to negative infinity. Okay, so this is also another interesting one to look at, right? So let's try our best to get this one out. That's it for divergent. Right, and then let's take a look at this third one here. All right, so this is what the oscillating sequence looks like. Now, oscillating sequences are sequences which are actually neither convergent nor divergent. So the convergent sequence we know approaches a particular value, right? And the divergent sequence similarly approaches values of either positive or negative infinity. But the oscillating sequence can't seem to make up its mind, right? It's divided into two types. This first type here is called the bounded and oscillating, right? An oscillating finite sequence, which is bounded, it is not convergent, as you can see on both sides. As the values of n approaches infinity, it doesn't seem like the function draws closer in any particular direction. It looks like a square, so it's kind of like bounded between a particular shape, and it's just moving back and forth, oscillating, and there's nowhere in sight it's ever going to converge. Kind of like somebody who don't want to change their mind and they move back and forth between two options, right? They are bounded and oscillating, but they are definitely not converging on a decision, or they are not diverging and giving up, if you want to think of it like that. That's a great way to think of it, actually. So an oscillating sequence. We have oscillating people in real life, actually. Yes, we do. All right, and the second type of oscillating sequences is oscillating sequence that is infinite. It is neither bounded nor does it diverge to positive or negative infinity. What do I mean by this? Well, this oscillating sequence, it's bounded because it maintains a strict shape even as the values of n increase, right? A rectilinear shape, you can see. But this one here, as the values of n increase on either quadrant, you notice that the shape is changing. It's ever changing, right? It seems to be increasing on end, but so it may look like a divergent quick sequence on top, and also like a divergent sequence on the bottom. But unfortunately, an oscillating sequence that is not bounded like this, neither does it diverge to positive infinity or negative infinity on either side. It just simply keeps increasing and increasing on both sides without ever approaching these values, right? So this is the second type of oscillating sequence. It's not bounded to a particular shape, but never does it diverge either to positive or negative infinity. So I would say that's your third most important type of sequence. The other two sequences, I'll just do a little quick chat about it. Periodic sequences. Periodic sequences, have you guys ever done music? How many of you guys play an instrument and they are like beats, you know, like when you're singing or you have to play the piano, you know, you hit that note on the piano. Can I draw a piano? It looks like a tooth, man. Whoa! Stick to maths, Miss Voodoo. So like, you know, they have a count system, right? So like if you're playing a note, you hit it and you count 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 1, 2, 3. That's called a periodic sequence, right? A periodic sequence is a sequence which repeats itself regularly. Its terms are repetitive. It's like the same thing occurring over and over and over, right? So this, if they had to describe this, this would be a periodic sequence with period 3, because it has 3 numbers in each of its repetitions, right? So frequently used in music. For those of you who want to know why is maths important to my life, why am I doing this subject? Yes, I drew it upside down, didn't I? But yes, it's very important in music. And the last one, I just realized I wrote back the same thing. So we will correct that now. I wrote oscillating twice. Why? Why is oscillating in my mind? I wonder. Well, the last one is actually called the alternating sequence, right? And an alternating sequence is just simply a sequence with terms that alternate between positive and negative values. For example, you can go from +1 to -1, then +1 to -1, and +1 to -1. Or you can go from +2 to -2. It could have had the vice versa. You could have been going from -2 to +2, -2 to +2, and so on. All right, which means I would need to change these signs for that sequence to be correct. -2 here, +2, right? So alternating sequences simply alternate between positive and negative values. And they actually can be convergent, they can be divergent, or they can be oscillating, right? So this is quite interesting. For example, something like this going between -1 to +1, if you had to draw those numbers on the, say, the y-axis, you know, this is +1 here, this is -1, right? And you had to draw the line y is equal to 1 and another line y is equal to -1, right? That could look like an oscillating, it's bounded, right? But it's oscillating, it's moving back and forth. So those are your 5 types of sequences. Now that you guys have a basic understanding of the different types of sequences we have at this level of maths, then we are going to begin getting into terms of a sequence and how do we even apply this in questions. Okay, so I'm going to clear my board now. Okay, give it a good clean. That was quick. I love using the whiteboard electronic eraser. It's fastest thing in town, right? All right, so we have sequences, and you guys realize that I said a generalization mathematical notation for sequences is just u to the n, right? So I'm going to highlight this here. So every time you see it popping in a question, you know that it represents just a simple sequence, right? So let's just take, for example, let's look at an example how we can understand sequences in questions, right? Okay, let's just say, for example, we have the sequence un, and it's actually equal to, we have an algorithm here, right? It's equal to 4n plus 2. And the question says, well, hey, since you have the algorithm for the sequence, can you write down, I don't know, say the first 2 terms? Write down the first 2 terms of that sequence. Well, the first term of the sequence will take place, right? The first term is going to take place when n is equal to 1. That would give us a value of u subscript 1. And because we have an algorithm here, we can use it and simply substitute that value when n is 1, right? We're going to get that 6. We're going to get u1, the first term, having a value of 6. And similarly, very nice, short, simple, sweet. The second term takes place when n has a value of 2. So u to the subscript 2 is just going to be equal to simple substitution. Where you see n, you just simply substitute that value of the term you're trying to find out. 4 2s are 8, and that's 10. All right. So the first 2 terms of the sequence are given by 6, 10. Remember, for sequences, we just have a set of numbers, right? It's definitely not a series where you would have like an addition sign in between. So take note of that when you are doing questions of this nature. All right, let's look at a little more difficult example. Right, so that's the basics. Let's apply that knowledge now to a situation where, I'm going to clear my board here as well. I'm trying to get rid of that, but it's not going away. So I'm going to clear my board. Right. And let's look at a second example here. All right. So choose this one. Wow. There we go. All right. Let's think of the sequence -1 to the power of n plus 1 by 1 over n. And for those of you who know me very well, you know where I get all my examples from. so you can follow along. All right, so for the sake of time as well, we are also going to just simply state the first, we are going to find the first two terms of this sequence, right? So term one, or first term, right? We have our sequence here. So to find U1 will take place when n has a value of 1. So I'll change my color here, right? Because we have some powers involved. So when n is 1, that's 1 plus 1 is 2. Our power has now changed, and we have 1 over 1. Now you all know negative 1 squared is just positive 1, and 1 divided by 1 is 1, so our answer is just 1. Let's find our second term. Second term U2. Okay. Now, when n is 2, that power changes to 3. And when n is 2, the denominator here is 2. Carrying on with life, negative 1 to a odd power will be negative, right? And we are multiplying that by a half. So our answer is negative 1/2. So therefore, our first two terms of that sequence will simply be 1 and negative 1/2. And then you can carry this on over and over and over to find the rest of the terms, right? So you can try those out if you would like. Now, what about if we were asked not to find the next few terms? What about if we had to find the nth term of a sequence instead of finding the first and the second and the third and the fourth and the fifth? What if we were asked to find the nth term of the sequence? How we would do something like that given the sequence? Well, let's look at an example here. Okay, clearing my board. Okay. So let's consider, all right, so let's consider we had a sequence with these values 2, 4, 8, 16, 32, 64, 128, and so on. Now, this is a very popular sequence. If you know it, you should already know what your answer is, but we will go ahead and work. Right, so what is our question? Our question is to find, the nth term. Now, they didn't say the fourth term or the third term or the fifth term. Remember, let's recall, let's go to my column here. If they ask us to find the first term, we find U1. If they ask us to find the second term, we find U2, and so on. So if they asked us to find the nth term, essentially what they are asking us to find is U subscript n. Right, so finding the nth term, they actually want to find out what is UM, or rather, what is the algorithm that the sequence is equal to. So we kind of have to look at this and figure out a pattern. Right now, you can look at this and observe that all of these numbers are written in powers of 2. For example, the first term, U1, if you were to call it that, U1 is written as 2 to the power of 1. U2, which is the second term, is written as 2 squared. U3 is written as 2 to the power of 3, and so on, right? So you'll notice that a pattern is building. So when n has a value, you notice that the power has the same value. So by the process of observation, it would imply that the nth term, this value here, seems to be 2 to the power of whatever the nth term is. So by a process of observation, you are able to pick up on that pattern and figure out the nth term of that sequence. Okay, so just a simple one to look at. This is how you would figure out the algorithm. If it comes, you have to look for patterns and make simple observations, and just take your time. All right. Okay, so moving on forward here. Now you can also define a sequence as a recurrence relation as well, right? Or a recursive sequence. For example, example 3. Let's understand this through an example, right? If you are given that, for example, you have U1 and you have U2 and you have U3, and they are the terms of a sequence, right? They are all terms of a sequence, right? So these three continues on and on and on and on till you perhaps reach U to the power of n. Not the power of n, sorry, U subscript n, right? All these are parts of the terms of the sequence, right? And let's just say they are giving you some values here. They are giving you U1 to have a value of 2. They are also going to give you, let me see, UN plus 1 has a value of 4, UN minus 1. All right. And that's it. They give you that bit of information. So they give us the first term in the sequence, 2. And they just give us, well, they didn't exactly give us an algorithm for the sequence UN. They gave us the n plus 1 term of the sequence. And it's also in terms of what we want to find, right? Well, what if instead of finding u to the n, they asked something like find the first, let's just say the first 3 terms. Find the first 3 terms of this sequence. That's the actual question. So you think to yourself, I don't exactly have u to the n. They have given me some stuff here, but they don't exactly want to find u to the n either. They want me to find the first 3 terms. Well, what are the first 3 terms to begin with? Well, for one, the first 3 terms are u1, u2, and u3. And we actually have the value of u1 already worked out for us. So we have that. So next we need to move on to the value of u2. Now, u2, how could we break that down? Well, u2 is also the same as u of 1 plus 1, isn't it? Yes. And looking at this, we can see the same format. It would imply that n has a value of 1 here. And if we were to substitute n being a value of 1 here, we would simply get 4 u1 minus 1. There we go. And we have a value for u1 being 2. So we simply substitute. And ta-da! 4 2s are 8 minus 1 is 7. We have found a value for u2. And I believe it will just be a repetitive process, or a recurrence relation rather, hence the word that we have sequences which can be recurrent, right? Recurrent or recurrence sequences, right? So let's just work out the last one. In order to get u3, that would be the same as u2 plus 1, where n would be our 2. Let me just highlight it. Right? These values here. Nice. And when n takes a value of 2, right, we will have u2 minus 1. And the question didn't originally give us that value, but we worked out u2 to be 7. So we can substitute that value in there. 7 4s are 28 minus 1 is 27. And there we have it. And this is what you call a recurrence relation, because you have to use your previous answer to get your next. Okay, so when questions like this come sometimes, you should take your time, because if you are doing this question to work all the way to the first 5 turns, I'd say if you make a mistake somewhere in the middle, you'll be losing some marks there. So take your time and be very careful. Okay, so there we go. Right. So I would allow you guys to take a short break here, or you can pause your video. And when we get back, we'll be moving on to convergence of a sequence with respect to limits. All right, so I'm just writing some basic notes from when you guys had to do Unit 1. You would recall that we had some limit laws. Just want to run through those quickly. All right, so if you recall, if you're finding the limit of 2 sequences and they are being added, you can simply expand that into the limit of sequence 1. As n goes to infinity, and plus the limit of the second sequence as n goes to infinity. And of course, if those sequences had values, numerical values, then you would just add them, whatever values they are. All right. Second law states that if you have 2 sequences and they are being multiplied by each other, all right, and you were to split them up, then by definition, the limit of the first one, if it were denoted by L1, and the limit of the second one, if it were denoted by L2, would just have to multiply the limits of both functions, sequences, sorry. And the third one, if you have 2 sequences and they are being divided by each other, the values will just be equal to the first limit divided by the limit of the second function. And finally, if you have the limit, or rather this rule applies to anything you're doing in most cases. If you are multiplying a sequence by a constant value k, right, you can just like when you integrate, you pull out those constants, you can pull out that constant, and it will just simply be equal to the limit as n goes to infinity of that sequence by the constant, right? K is a constant. So recall these main limit laws before you move forward. And also it might help to just recall a bit of or recap rather, a bit of limits from Unit 1 before moving forward into convergence of a sequence in Unit 2. Okay. Right, so we are going, let's erase that from the board actually. All right. Trying to get to the top of the board so we have more space, so I don't have to continuously erase. Okay, so let's look at some questions here. So what if we have a simple sequence Nice little baby one. It looks like this. All over. Okay, and the question is asking us to simply find the limit of this sequence as n approaches infinity. What will its limit look like? Is it convergent? Is it divergent? Well, let's get into it. As you guys recall, when you were doing limits, one of the most popular things to do to get a limit that has so many powers involved in n is to divide both the numerator and the denominator by that highest power of n you can find. So in this case, we are going to divide by n squared, right? Which will give us 8 on our numerator over 6 plus 3n over n squared will give us 3 over n, and then 2 divided by n squared, right? And we do this because had we used or substituted n and being infinity on the numerator would have gone to infinity, and clearly the denominator would have gone to infinity. So we would have more of like an indeterminate form where you get an infinity over infinity. Recall your indeterminate form, 0 over 0, infinity over infinity. Indeterminate can't fit, but you just make sure you are able to recall that, right? So getting into the nitty-gritty of it, we try our best to divide by the highest power of n and see where that takes us. All right, nice. So that gets us into something that we can already see is merging or converging rather into a value. And if you want proper notation, you will make sure you write the limit as n goes to infinity using your rules of every single term in this question, right? Some students just simply write the answer off the bat, but sometimes it doesn't hurt to understand what you're doing in the beginning by writing it all out. Okay. And finally, that last one, using the rule of constants. Oh, almost forgot my limit sign there. There we go. So you can tell that as n approaches infinity, you will get 1 over 0, right? Sorry, 1 over infinity, which is equal to 0, which is what I wanted to say. So this becomes 1 over infinity as n approaches infinity, and that just tends to 0. So this entire term just goes to 0. Similarly here, as n approaches infinity, this entire term goes to infinity, so it just goes to 0. Sorry, I keep saying infinity when I mean 0, man. Anywho's, numerator, there is no n present in this term, so that limit maintains a strict value. If this were a sequence in and of itself, it would definitely be convergent because clearly it's just 8. And similarly, denominator, you have that value of 6 because there's no n to go to infinity here. So your answer is either 8 over 6 or 4 over 3. And clearly, this sequence is converging. How do we know it's converging? Converges or convergent or converging, whatever you want to write. It's converging because we have a limit value where you have L being equal to 4 and 3. You are actually able to get a numerical value for its limit. That's how you know that a sequence converges or is said to be convergent. Okay, so take your time when you're doing questions like this. Now, one thing I would like to also have you guys learn today, if you have never learned it before, is a rule that if you are planning to do maths at the university level, this is going to rock your world for quite a while, because it pops up in an entire course, right? And it's called the Hopital's rule. Yeah, when I first heard the word, I took a while to get accustomed until I realized the entire semester I was going to be hearing the word, and it just stuck in my head. L'Hopital's rule. You learn to say it eventually, don't worry. So this is supposed to be covered in Unit 1, but if it was not touched upon, L'Hopital's rule is simply applied. When do you apply it? Well, applied when? When you say, when do we apply this? Well, let's just say you have the limit of, you have a function on the numerator, you have a function on the denominator, two different functions, and you want to know what's happening as x approaches a value of, say, a. Not in particular, it has to be infinity, right? Just a value a, right? And no matter how hard you try, you try dividing top and bottom by the highest power of n, you try everything you can, you factorize, you cancel as much as you can, and no matter what you do, you always seem to be getting 0 over 0 or any indeterminate form, as a matter of fact, right? So indeterminate, yes, I teach maths. I should be good in English, shouldn't I? But spell it out. All right, so whenever you have to find the limit of a particular sequence, and you notice that no matter what you try, numerator and denominator, you're going to get that 0 over 0 indeterminate form, then you can try something called the Hopital's rule. You can try. I'm not saying it's always going to work, but you can try. Okay, and well, it should work actually. It's supposed to. Hence the point. Yes. Anyways, then what you can do, the Hopital's rule simply states that anytime you get this result from just trying a regular limit, you can just go ahead and try this instead. You differentiate your numerator. Yes, differentiation. I know it's coming back to haunt you. Differentiation is nice though. It's really nice, right? So if you can't figure out this, then work the differential of both your numerator and denominator, and hopefully you get an answer. All right, so basically once you have an indeterminate form, you can find the limit by simply differentiating the numerator and denominator. The rule is supposed to work every time, right? And if it doesn't, let's just say it doesn't, and you differentiate and you still end up getting an indeterminate form, then what do? You can differentiate again until you eventually end up getting your answer. So this is what I meant by it doesn't work, right? Sometimes you still get a case where you're going to get 0 over 0. Just try differentiating over and over and over. Students tend to use this rule for everything, and there's a condition when this rule can be used, and the condition is that upon your first initial evaluation of applying the limit, you must get the indeterminate form. If you get a case where you have like 1 over 0, that's you cannot use a Hopital's rule. You can't, right? Because this is not an indeterminate form, right? So be very careful when applying this. You must get your 0 over 0, infinity over infinity. It must be indeterminate. Okay. All right. So let's look at an example of this application. All right. So let's just erase this. All right. Moving on to an example. So let's just say you have the sequence u to the n equals 6n over 2n minus 1. All right. And yeah, let's try our best to see how we can find we want to find the limit as n approaches infinity of our function, right? So the limit for this function will be n approaches infinity of 6n all over 2n minus 1. Now, as you can see here, the highest power is n. And if, let's just say if we had to try, when we divide by the highest power of n on the numerator, you would get 6. On the denominator, you would get 2 minus 1 on n. And then as n approaches infinity, you'd notice that you end up getting 6 over 2 minus 1 on infinity, right? Which is not exactly the case scenario that you're looking to happen. So you can see clearly that you are going to get this function being in the form of infinity over infinity, no matter how hard you try. If you were to directly apply infinity here, 6 times infinity is just infinity. 2 times infinity is infinity minus 1 will still be infinity. You'll see that form is being highlighted here. And if you choose division by the highest term, it does not help very much, right? So it is clearly in an indeterminate form. So hence, what you can do is apply the Hopital's rule and make sure you state that when you're doing your question. So using the Hopital's rule, right, you are now going to be able to differentiate both your numerator and your denominator. If you let f of x be equal to 6n and g of x be equal to 2n minus 1, then you have the limit as n approaches infinity of your function, right, also being equal to the same as the limit as n approaches infinity of differential of that function over the differential of this one. Now, since the first order numerator is given by 6n, the differential of that with respect to n is simply 6. And on your denominator, the differential of this g function with respect to n is simply 2. Differential of a constant is 0. And clearly, we can see that value is 3. So therefore, the limit of our sequence as n approaches infinity using the Hopital's rule is a value of 3. And because we got a numerical value, what type of sequence is this? That's correct. It is a convergent sequence, right? It converges to a actual number. All right, guys. So I hope that you guys are getting a bit better with sequences and some points to know that you guys should understand that a finite sequence contains only a finite number of terms. The same is true for an infinite sequence. It will contain an infinite number of terms. If a sequence is convergent, it approaches a fixed value, right? In a case like this. Any sequence which does not converge to a value is said to be divergent, right? Hence the reason why a lot of the times you would not be able to find the limit. When you can't find the limit, it simply means there is none. There exists no limit. It's divergent, right? A periodic sequence repeats at regular intervals. Oscillating sequence, the one that's bounded between two values, I'll never forget that. And an alternating sequence that changes signs back and forth, positive and negative, right? Also note that a sequence is written as a list of numbers with a comma, not a addition sign, and the notation is given by u to the n. All right, and sometimes you can get a recurrent or recursive sequence that keeps using the previous value to work out the following value. So once you're able to successfully understand those basics of sequences, then you have successfully, I would say, completed the basics on understanding what a sequence is, how to apply the Hopital's rule, and how to find the nth term of any given sequence. So if there are no more questions, I would give you guys some for homework to try on your own time, and we'll be moving on to series in our next video. So I wish you guys all the best. Remember, work hard but play harder. Life is not about books only, all right? There's a lot out there. All the best. Take care, bye.